Hello, everybody. Welcome back to the next lecture from AAT Learning Hub. Today, we are going to continue our discussion of cardiac cycle and attempt to make sense of the intimidating Wiggers diagram that I mentioned in my last lecture. Wiggers diagram is named after its creator, Dr. Carl Wiggers, one of the greatest cardiac physiologists of all times. It is a unique diagram that has been used in teaching cardiac physiology for more than a century. It is a pictorial representation of the physiological processes that occur in the heart and demonstrates the pressure and volume changes in the atrium, ventricle, and the aorta during one cardiac cycle. The diagram represents simultaneous electrical and mechanical events in the heart with six stacked graphs showing the aortic pressure, the atrial pressure, the ventricular pressure, ventricular volume, electrocardiogram, and lastly, the heart sounds. Before we begin cracking, it is important to be familiar with the cardiac anatomy and events of the cardiac cycle. Please refer to my previous lectures in this channel to brace yourself. To decode Wigger's diagram, we also need to refresh the essentials of electrocardiogram. We know that the specialized cells of the heart's electrical conduction system work together to generate impulses that cause the heart to contract and relax, resulting in the rhythmic beating of the heart. The depolarization and repolarization process enables the cells to contract and relax in a coordinated manner. Depolarization causes an electrical impulse to be generated, making the cardiac cells less negative and contract. Repolarization is the return of the ions to their previous negatively charged resting state, which corresponds with relaxation of the myocardial muscle. The ECG waveform shows the pattern of electrical impulses produced by the heart, including the depolarization and repolarization phases. P wave refers to atrial depolarization. The QRS complex refers to ventricular depolarization. Repolarization of the atria is not seen as it is hidden by the QRS complex, and T wave signifies ventricular repolarization. This is our original Wiggers diagram. Let's break it down into simple concepts and individual waveforms and try to understand each of them clearly. A point to note is that the events in the graphs represent the changes happening in the left side of the heart. The pressure ranges on the y-axis from 0 to 120 millimeters of mercury, and the ventricular volume ranges from 50 to 130 milliliters. Now let's begin dissecting the Wiggers diagram starting with the ECG. First step would be to label the ECG waveform with respect to the phases of the cardiac cycle, starting with the atrial systole, atrial diastole, ventricular systole, and ventricular diastole. We know from our previous lecture that each of these phases are divided into subphases. Ventricular systole into isovolumetric contraction, rapid ejection phase, and slow ejection phase, and ventricular diastole into isovolumetric relaxation, rapid filling phase, and slow filling phase. The first phase is that of the atrial contraction, in which the mitral valve opens and blood rushes into the left ventricle. The next is the ventricular systole, consisting of isovolumetric contraction, rapid and slow ejection phase, in which the ventricle contracts, pumping blood into the aorta. The next phase is the isovolumetric relaxation phase, when both the mitral and aortic valves are closed and ventricle relaxes in a closed chamber, following which the mitral valve opens and blood rushes into ventricle, filling it once again, and the cycle repeats itself. Starting with the aortic pressure waveform, the aortic pressure is 80 millimeters of mercury during diastole. During the ejection phase of the left ventricle, the aortic pressure rises to 120 millimeters of mercury as the blood is pumped into the aorta. During the isovolumetric relaxation phase, the aortic valve closes, causing the dichroic notch in the aortic pressure curve. The next waveform is the left ventricular pressure tracing. During isovolumetric contraction, LV contracts in a closed chamber with both the mitral and the aortic valves in closed position. The pressure inside the LV chamber rises rapidly, and when the pressure becomes more than that of the aorta, the aortic valve opens and rapid ventricular ejection begins, followed by slow ejection phase. At the end of the ejection, the LV pressure drops below the aortic pressures, the aortic valve closes, and isovolumetric relaxation phase begins. As the pressure in the LV falls below the atrial pressure, the mitral valve opens and starts the rapid and slow filling of the ventricle. As far as the atrial pressure waveform is concerned, during atrial contraction, the pressure in the atria is more than that in the ventricle, and the blood empties into the ventricular chamber. During isovolumetric contraction, LV contracts in the closed chamber, the LV pressure rises and pushes the closed mitral valve into the atrium, causing an increase in the atrial pressure. During the ejection phase of the ventricle, the atrium gets filled with blood and the pressure in the atrium slowly rises. When the pressure is more than that of the left ventricle, the mitral valve opens and the filling phase of the LV begins. So, when we translate this into right atrial activity, the jugular venous pulse can be studied. In the waveform, the A wave corresponds to atrial contraction. C wave corresponds to the bulging of the closed tricuspid valve into the right atrium during isovolumetric contraction of the right ventricle. The V wave is due to passive atrial filling. The next waveform is that of the ventricular volume. There is a huge drop in the ventricular volume during the rapid ventricular ejection phase because the blood is being pumped out of the ventricle into the aorta. The ventricular volume slowly increases as the mitral valve opens and blood from the atria is pumped into the ventricle again, thus increasing the ventricular volume. Heart sounds are created from blood flowing through the heart chambers as the cardiac valves open and close during the cardiac cycle. The first heart sound is heard when the atrioventricular valves close shut during isovolumetric contraction. It is called the lub sound. The second heart sound is produced when the semilunar valves close during the isovolumetric relaxation phase. This produces the dub sound. The third and fourth heart sounds are usually abnormal and are not heard in healthy individuals. The third heart sound can sometimes be heard during the rapid filling phase and may be physiological or pathological. The fourth heart sound is always pathological and occurs during the atrial contraction against a non compliant ventricle. Now let's put together all of these waveforms into one neat, concise picture. Bingo, it's the Wiggers diagram. So first, we saw the electrocardiogram and then moved on to the aortic pressure tracing, followed by the ventricular pressure tracing and the atrial pressure curve. Subsequently, we saw the ventricular volume curve, and then we concluded with the phonocardiogram or the heart sounds tracing. Hooray! We've now successfully unraveled the Wiggers diagram. Hope you all understood the core concepts of cardiac cycle and found this lecture useful. Please do like, share, and subscribe to our channel for more knowledge power. See you next time with another interesting topic. Until then, stay focused and stay curious. Bye bye.